We are coming towards the application part of it now, and this application we have in mind is for demonstrating how can we achieve low latency using edge clouds. Particularly, we have augmented reality and virtual reality applications in mind, but today we'll be showing you the object detection, which is just a precursor to what we would like to achieve using the augmented reality application. So here is with me Vuyank, and I'm Sumit, and we are part of WinLab and Cosmos. So those of you who were here yesterday, this might be a repetition, a little bit of it. So we would like to envision that, assume that there is a network layer, which is this edge compute layer, which is, as you have seen, like the medium nodes and the large nodes where we can aggregate the traffic. And if you would like to do anything related to road safety or smart traffic intersection, which you will hear more about from the next speaker, we would like to say that can we divide these road into segments, and is it sufficient to just get the information from one of these road segments, or is it necessary that you should be able to collect the information from all these road segments and pass it along? For example, a car is driving behind you at a fast speed, and would you like to get the information about it so that when you change the lane, you should be able to be aware of that, or you should be cautious. There is a car which is applying brake, which is ahead of you, a half mile ahead of you, and as you know, like because of the back pressure, you'll have to apply the brake as well. So would you like to get those kind of information, and can we do that those kind of processing? And those are, of course, little and trivial examples, but we'd like to go deeper into that by creating, for example, let's say, can we create a 3D point cloud so that you can get all the information about not just the vehicle in front of you, but much ahead of you, and in a much nicer way on your screen. So for doing that, we assume that the cars have some kind of functions. For example, the augmented reality functions. There are some kind of display or novel methods to display that information. The car also had some kind of compute, but we'd say like most of the compute will happen at the edge cloud. Then if we can use the infrastructure support using the Cosmos, which essentially is to fetch all these images which we take from the cameras deployed across the intersections and beyond, and collect them at the edge cloud, not just these, and can we use some of the more information from the vehicle support and collect all this information into these edge clouds, and then finally process it, fetch it back to the users in low latency. For example, some other information can be the traffic light and sensory information from the infrastructure deployed to be deployed in New York for Cosmos, and then do some kind of analytics and mapping and all sort of application use cases you can think of using this data, present it in a coherent way, in a way that people can understand, have a meaningful impact of it, and finally get back a view which you essentially is nothing but a coherent view of all the vehicles around. So this is our understanding of what we would like to achieve, and basically our motivation to achieve low latency application. And what we are going to show right now is the object detection part of it, which is can we do everything in real time, and how far in latency can we go low. So I would hand over to Yang, who will talk next. Thank you.
So then I'll give more details about the demo itself. So first, let's take a look at the demo setting. So at the Cosmos testbed, it has a multiple cameras at the different locations. In this demo, we are using the one at the second floor of a building at the Amsterdam Avenue. So for this camera, it can support multiple different resolution with different frame per second. So in this demo, we are using the resolution of 720p resolution at 10 FPS. And there is a dedicated link bandwidth between this camera to the compute node at the Cosmos testbed. And for the hardware part, we are using the V100 GPU. So based on the profiling result from NVIDIA, as we can see here, the first is the performance of the Tesla V100 GPU. It basically can deliver around 47 higher throughput than a normal CPU, I mean the Xeon CPU. So here is a demo. I'll try to show how to use a machine learning or deep learning to enable this vehicle or pedestrian detection, and also put a mask in it in real time. So, because it's a little difficult to ship the video from the camera to here due to the limited bandwidth. So we record this video yesterday, as we can tell the date and the time at the left corner. Let me play it. So in this demo, it takes the real-time video as the input, and then after the image processing part with deep learning, specifically it's a mask RCN, so it can do the vehicle and pedestrian detection, and also as we can see here, it can put a mask on it, exactly cover its shape, not only just put a rectangle around it. So we can we think to exactly identify the shape or the mask of those objects. It could be useful for a lot of applications. So for example, those traffic management or the safety warning, those sort of things. And as we can tell in the video, in the most of the time, it can accurately detect those big cars, but yeah, sometimes it will miss those teeny objects, especially those small persons. Okay. So next, I'll give more details about the backend technology of, the deep learning part. To enable this real-time detection. So this deep learning neural network is named Mask RCN. It has been proposed by the Facebook lab 2 years ago. So basically, it's let me show you here. So it takes the real-time video as an input, and firstly, it passes through a backend network named ResNet. So in this part, it basically tries to extract those feature maps, and then we move to the second part, feature parameter network. This part is again to extract the feature map, but the difference is in this part, it tries to focus on those teeny objects in the frame. And then we move to the third part, region proposal network. So so the definition of region proposal is a possible region that an object might be in. So in this network, it takes a brute force way to firstly enumerate all the possible region proposal over a frame. And then this network will try to evaluate each region proposal to give each of them an object, a score, to evaluate what is the possibility that region proposal may have an object. And then it will redefine the bounding box. So the region proposal itself is a rectangle, but it may try to refine this rectangle to that include that object. And then we move to the post processing. So in this part, it'll try to drop those region proposal with low object score, and also drop those region proposal whose bounding box is out of the row frame. And then we move to the ROI part. So in this network, it'll try to resize all the region proposal to a same size. And then finally, we move to this part. So in this network, it basically tries to predict upon each region proposal filtered by the previous network, and tell what is the object class for that region proposal. And also, at the meantime, it will predict the mask and put it on that region proposal. So finally, let's take a look at the latency evaluation. So here we show the latency performance over around in around 5 minutes, and we record end-to-end latency. So end-to-end means we start record by taking I mean when we take that frame as an input and end at we finish the image processing computation and then put a mask on it. So the average of the end-to-end latency is around 95 milliseconds, basically 10 frame per second. So we believe this latency can basically satisfy the self-driving applications in a city environment where the car moves in a slow speed, like within 30 miles per second. But if we consider the case when the car drives in highway with a higher speed, say 60 miles per second, we can further optimize this computation with a distributed GPU computing. That is a part of work we are working on right now. Yep, so that's it.
Right, yeah, so if you have any questions.
So yeah, if you have any questions.
Okay. Use 10 frames per second is because of the latency is around 100 milliseconds.
Right. So we can also take the input with say 30 frames per second as an input, but in that case, due to the limited computation capability here, we need to selective the frame. So the most straightforward method is to pick 1 out of 3 frames, right? But we can definitely introduce more computation capability here, or say here we are doing the distributed GPU computing. That could be one solution. Right. Yeah.
Yes, still, not a millisecond versus 0.5 milliseconds.
Yeah, so we think there could be many other more interesting applications with this real-time video input. So yeah, we are happy to discuss more about this if any of us have some good ideas. Yeah, thank you.
Thank you.